Hello everyone, my name is Aqib and today I'll be talking to you about fracture mechanics in the light of thermodynamics. Now for this video I will assume that you are familiar with the basic concepts of fracture mechanics, and I'll try to rederive some of the results which we usually derive in a different way in, in our mechanics setting by using thermodynamics. So to this end, let me begin by just reviewing some of the thermodynamics that we are going to need. So let us assume that there is a system, there is a block, and there is a system, and the potential energy of the system U is actually a function of the entropy and volume. So for example, uh, U can depend upon entropy and volume and not some other parameters. I'm assuming it as a ideal gas, if you want to say it, think it like that. So if that is true, then du should be equal to del u over del s at constant volume times ds plus del u over del v at constant entropy times dv. This is just chain rule. Now let me define del u over del s at constant volume as my temperature and del u over del v at constant entropy as minus of pressure. Now this may seem a bit strange because I am kind of going the opposite way, but it can actually be shown that this definition of temperature recovers our own intuitive understanding of what temperature is or what pressure is. So for example, the degree of hotness and coldness and so on. But by the way, this is the most I'd say this is a more rigorous mathematical definition of what temperature and pressure are. Okay, but we'll not delve a lot into it. What I'm going to now say is that du equals tds minus pdv, which is basically the first law of thermodynamics. Clearly, I have written du in terms of the differentials of entropy and volume, and the equation will yield very simple results for a system which have constant entropy or constant volume. So for example, if the system has constant volume, then the second term drops and my du is just tds. In the other case, when ds is 0, my du is just minus pdv. Now I want to massage it further to write it in terms of differentials of t and p, for example, instead of s and v. So to do this, let me introduce something called as Legendre transforms. And what they do is that they change the differentials from one quantity to its conjugate. So these pairs are conjugate quantities. P and V are conjugate, T and S are conjugate, and so on. So how do you achieve this Legendre transform? Well, you just choose a new variable. Let's say f u minus which variables you want to flip. So in this case, let's flip t and s. So u minus ts. So now what will happen is df is du minus tds minus sdt, and now you will realize that if you plug in the expression of du from equation number 1, you will actually cancel out the tds term and you will end up with minus sdt minus pdv. This f, by the way, is called as the Helmholtz free energy. Helmholtz free energy. Yeah. Similarly, if someone wants to flip P and V, for example, he'll have to uh, make up a new quantity called enthalpy and do U plus PV. And when you take the differential by the similar logic, you will end up with TdS plus VdP. This is enthalpy. Now, I mean, we are all familiar with all these notions, the free energy, the Helmholtz free energy, the enthalpy, but this is in a different light, that what they are actually doing. So there is one more free energy, and that is called the Gibbs free energy, G, that is actually obtained by using both the transformations simultaneously. And once you do this by similar logic, you perform the differentials of du minus tds minus sdt minus pdv plus vdp, you will end up with minus sdt plus vdp, and this is called the Gibbs free energy. Okay, why am I doing all this? What does it have to do with fracture mechanics? Well, now having assembled all these tools, what I'm going to do is the following. I'm going to assume there is a system which is in contact. So the system will look like following. There is a body like this, and there is another body like this, and let's say they are in contact over an area A, right? And let's say that the top body is being pulled up with a displacement delta, right? So I mean, in fracture mechanics we usually talk about displacement control mode or the load control mode, but so this is very similar to that. This is the displacement control. Now in this system I can say that the potential energy U is a function of two things. One is A and one is delta, obviously. Also, the potential energy has two components: the elastic potential energy and the surface energy. So the elastic potential energy is just due to stretching of the material due to deformation effects. The surface energy is due to this contact, and this is equals minus gamma times A, where gamma is the surface energy. Now per unit area. Now why is this minus? Well, let's talk about the definition of the surface energy itself. The surface energy of a body is defined as the energy, I am sorry, the surface energy of contact is defined as the energy you have to apply externally to break the contact. Now if you apply an energy gamma A externally, then the net energy of the system becomes minus gamma A plus gamma A, so that the total becomes zero after the bodies are separated, which it should be. This will not happen if, for example, you assume a plus sign here. So that is why minus sign is put in here. Okay, that's all fine. Let me now just talk about the elastic energy part here. Let me write down the following. du elastic equals del u elastic over del delta at constant A, d delta, plus del u elastic over del A at constant what, delta, dA. Okay, just the elastic part. Now by definition, this is the strain energy release rate, SERR, your G which we are familiar with from fracture mechanics. And why is that? Because that's the whole definition, the rate of change with area of the elastic stored energy of the body at constant delta. That's your G. Okay, so what does this equation give me? Well, it just says that if you have a constant delta, that is d delta 0, so I'd say displacement control, d delta is 0 because delta is defined, so my due is just g times dA, right? And therefore I can directly say that my G is del UE over del A at constant delta. Okay, that's fine, but that's that whole definition of it, right? I mean, I am just recovering the definition. It is not anything very new to us. But okay, fine. Let me do something which might not be so trivial. Let's try to do load control. So first of all, you have to realize that what is the load. Load is P. If I say the load is P, that is just del UE by del delta at constant A. I'll let you think about it, but it basically follows from the definition of, I mean, um, the whole definition of work done. If you think about it, I'm sure you can convince yourself this P is this thing. So that if P is this thing, you can see that your DUE is P d delta plus G dA from here. Fine. Now for the load control case, what I want to do is to change my dependence, the differential dependence on delta to P. So as you might have guessed is, now we are going to use our Legendre transformations to change this dependence. So now let me define a new quantity UC in this way, minus P delta, because I want to switch this dependence. UC I'll call as complementary strain energy. The physically you can see it as follows. So if you have your stress strain curve, let's say this is stress strain curve, and it goes something like the following. Then yeah, sorry. Then this area is your U elastic, and this area is your UC. The P delta, I'm sorry, this should be P delta minus UV. I'm sorry. P delta minus UV. Sorry. Yeah. Okay. Once we define a Legendre transform like this, now what we are going to do is to take DUC, the differential of the complementary strain energy, and we define it as P d delta minus delta dP minus DUE, which is minus P d delta minus G dA. And I see that P d delta cancels, so this is minus delta dP minus G dA. I'm sorry, I don't know why I put this A here. Okay, now if dP is 0, what will happen is DUC is minus G dA, and therefore G will now becomes minus DUC over dA. So therefore, by defining UC in this way, I recover my old definition of the strain energy release rate for constant loads. So I hope this was helpful to see it in a different light, and the fact, and to basically appreciate the fact that my G, the definition of G remains the same, just that by changing load from constant load mode to constant displacement mode, you can get these two different definitions, and they are very much tied together. And in the bigger scheme of things, even this potential energy is just a Legendre transform of the strain energy. The book that I have used for this is Maugis Contact, Adhesion and Rupture of Elastic Solids. I'll add that in the description. So thank you very much.